Identifying network management protocols and features. Proper network management is a critical component of an efficient network. Network administrators need tools to monitor the functionality of the network devices, the connections between them, and the services they provide. SNMP, or the Simple Network Management Protocol, has become the de facto standard for use in network management solutions and is tightly connected with remote monitoring, or RMON, and management information bases, or MIB. Each managed device in the network has several variables that quantify the state of the device. You can monitor managed devices by reading the values of these variables, and you can control managed devices by writing values into these variables. So this section introduces SNMP and describes the differences between SNMP versions 1, 2, and 3. The role of MIBs in SNMP and RMON's monitoring is described. The Cisco Network Discovery Protocol, or the CDP, is introduced. This section concludes with a description of methods for gathering network statistics. Let's get started. Network management architecture. So this figure illustrates a generic network management architecture. So the network management architecture consists of the following. So first, there should be an NMS, or the Network Management System. This is a system that executes applications that monitor and control managed devices. NMSs provide a bulk of processing and memory resources that are required for network management. So next would be the Network Management Protocol. So a protocol that facilitates the exchange of MIB information between the NMS and the managed devices. So this includes the SNMP, or the Simple Network Management Protocol, the MIB, or the Management Information Base, and RMON, or the Remote Monitoring. Also, there should be managed devices. So a device such as router, computers, and nodes, those are managed devices. Okay, so these are managed by the network management system. You also have management agents. So these are software on managed devices that collects and store management information, including SNMP agents and RMON agents. Next would be the management information. Okay, so data that is interest to a device management, usually stored in the MIBs. So a variety of network management applications can be used on network management systems. The choice depends on the network platform, such as hardware and operating systems. The management information resides on network devices. Management agents that resides on the device collect and store data in a standardized data definition known as the MIB, or the Management Information Base. Okay? Now, the network management application uses SNMP or other network management protocols to retrieve the data that the management agents collect. And the retrieved data is typically processed and prepared for display with the GUI, or graphical user interface, which allows the operator to use a graphical representation of the network to control managed devices and program the network management application. Okay, so let's have the Simple Network Management Protocol, or SNMP overview. Okay, so SNMP has become the de facto standard for network management. So SNMP is a simple solution that requires a little code to implement, which enables vendors to easily build SNMP agents for their products. So in addition, SNMP is often the foundation of the network management architecture. So SNMP defines how management information is exchanged between network management applications and management agents. Now, this figure here shows the terms used in SNMP. Now they are described as follows. So let's start with the manager. Okay. So the manager, a network management application in an NMS, periodically polls the SNMP agents that reside on the managed devices for the data, thereby enabling information to be displayed using a graphical user interface or GUI on the NMSs. A disadvantage of periodic SNMP polling is the possible delay between when an event occurs and when it is collected by the NMS. So there is a trade-off between polling frequency and bandwidth usage. Okay, so next would be the protocol. So the SNMP is a protocol for message exchange. It uses user datagram protocol or UDP, so to send and retrieve management information such as the MIB variables. Next would be managed devices. Okay, a managed device, routers, switches, computers, these are being managed by the manager. Okay, and also you have management agents or agent. These are SNMP management agents reside on the managed devices to collect and store a range of information about the device and its operation, responds to manager's request, and generate traps to inform the manager about certain events. Now, SNMP traps are sent by the management agents to the NMS when certain events occur. So trap notifications could result in substantial network and agent resource savings by eliminating the need for some SNMP polling requests. And the other one would be the MIB, or the management information base. So the MIB, okay, or the management agent collects data and store it locally in the MIB. So MIB is basically the storage or the database of objects about the device. Okay. Now, community strings, which are similar to passwords, control access to the MIB. So to access a set of MIB variables, the user must specify the appropriate read or write community string, otherwise access is denied. SNMP version 1 message types. So the initial version of the SNMP version 1 is defined in the RFC 1157, the Simple Network Management Protocol or SNMP. So the protocol simplicity is apparent by the set of operations that are available. So this figure here shows the basic SNMP messages which the manager uses to transfer data from the agents, okay, to the manager. Okay. Now, these messages are described as follows. So first, you've got get request. So used by the manager to request a specific MIB variable from the agent. Next would be get next request. These are used after the initial get request to retrieve the next object instance from a table or list. Next would be set request, used to set a MIB variable on the agent. And then get response, used by agent to respond to a manager's get request or get next request message. And the last one would be trap, used by the agent to transmit an unsolicited alarm to the manager. So a trap message is sent when specific conditions occur, such as the change in the state of the device, a device or component failure, and an agent initialization or restart. SNMP version 2. So SNMP version 2 is a revised protocol that includes performance and manager-to-manager communication improvements on SNMP. So SNMP version 2 was introduced with RFC 1441, Introduction to version 2 of the Internet Standard Network Management Framework. But members of the IETF subcommittee could not agree on several sections of SNMP version 2 specifications. So primarily, the protocol security and administrative needs. So several attempts to achieve acceptance of SNMP version 2 have been made by releasing experimental modified versions. So commonly known as the SNMP v2, okay, SNMP v2U, SNMP v1 Plus, and SNMP v1.5, which does not contain the disputed parts. So the community-based SNMP version 2, or the SNMP version 2C, which is defined in the RFC 1901, Introduction to Community-Based SNMP version 2, is referred to as SNMP version 2 because it is the common implementation. Okay? Now, the C stands for community-based security. So, because SNMP version 2C uses the same community strings as SNMP version 1 for read and write access. So, SNMP version 2 changes include the introduction of the following two new message types. So basically, you've got this get bulk request, which is used for retrieving large amounts of data, such as tables. Okay, this message reduces repetitive requests and replies, so thereby improving performance. Next one would be the inform request, used to alert the SNMP manager of the specific condition. Unlike unacknowledged trap messages, inform request messages are acknowledged. A managed device sends an inform request to the NMS. The NMS acknowledges the receipt of the message by sending a response message back to the managed device. So another improvement of SNMP version 2 over SNMP version 1 is the addition of new data types with 64-bit counters, because 32-bit counters were quickly overflowed by fast network interfaces. SNMP version 3. So SNMP version 3 is the latest SNMP version to overcome the version 2C. Okay? And it became a full standard. So each introduction has moved SNMP version 1 and SNMP version 2 to historic status. Now, we have two types of status for the standards. So one mentioned was historic. That means the old version was replaced with a new version. So something like SNMP version 1, okay, is already historic. Okay, SNMP version 2 is already historic. And at the same time, they are obsolete because they are obsoleted by a new releases or a new version. Okay? Now, SNMP version 3, which is described in the RFC 3410 through 3415, adds methods to ensure the secure transmission of critical data to and from the managed devices. So, SNMP version 3 introduces the following three security levels here. So, you've got no auth, no priv. So, that means without authentication and without privacy or encryption. Next would be auth, no priv. Okay, so there is an authentication but without privacy. Authentication is based on the hash-based message authentication code message digest 5 or the HMAC secure hash algorithms. Okay, you also have the auth priv. So with authentication as described early and privacy using the 56-bit cipher block chaining data encryption standard. So security levels can be specified per user or per group of users via direct interaction with the managed device or via SNMP operations. So security levels determine which SNMP objects or user can access for reading, writing, or creating, and the list of notifications that users can receive. MIB definition. Okay, so the Internet MIB hierarchy. Now, as shown here in the figure, the MIB structure is logically represented by a binary or a tree, okay, hierarchy. So the root of the tree is unnamed, okay, and splits into three main branches. So basically, Consultative Committee for International Telegraph and Telephone, the CCIT, okay, the ISO, and the ISO CCITT. Now, these branches and those that fall below the category are identified with short text strings and integers. Now, text strings describe object names, whereas integers form object identifiers that allow software create compact encoded representation of the names. Now, the object identifier in the Internet MIB hierarchy is the sequence of numeric labels on the nodes along the path from root to the object. The Internet standard MIB is represented by the object identifier, something like 1.3.6.1.2.1, which can also be expressed as iso.org.dod.internet.mgmt.mib. MIB definition. So the Cisco private section of the MIB tree contains private managed objects, which are introduced by Cisco, such as following objects for routers. So small, medium, large, and huge buffers, primary and secondary memory, and proprietary protocols. So private definitions of managed objects must be compiled into the NMS before they can be used. The result is output that is more descriptive with variables and events that can be referred to by names. Okay? So the private extensions to MIB2, something like you have this 1.3.6.1.4.1.9. Or it is the iso.org.dod.internet.private.enterprise.cisco. So that is within the tree here. MIB definition. So let's have an example. So this figure here depicts the SNMP MIB variable retrieval in action. Okay. Now in this example, the network manager, okay, wants to retrieve the number of errors on the first interface, starting with interface number 0. Okay. Now the valid range of interface numbers is 0 through the maximum number of ports minus 1, because we've started with 0. Okay. Now the manager creates the SNMP get request message with reference to the MIB variable, and that is 1.3.6.1.2.1.2.1.20.0. Okay, so which represents interface outgoing errors on interface 0. Okay, the agent creates the SNMP get response message in response to the manager's request. The response includes the value of the referenced variable. Now in this example, the agent returned value is 11. Okay, indicating that there were 11 outgoing errors on that interface. RMON1, or the remote monitoring. So the key point would be RMON is an MIB that provides support for proactive management of LAN traffic. Okay, so RMON standard allows packet and traffic patterns on the local area network segments to be monitored. So RMON tracks the following items. So number of packets, okay, packet sizes, broadcasts, network utilization, errors and conditions such as Ethernet collisions, statistics for hosts, including errors generated by hosts, busiest hosts, and which hosts communicate with each other. So RMON feature include historical views of RMON statistics based on user-defined sample intervals, alarms, that are based on user-defined thresholds and packet capture based on user-defined filters. Now, the RMON groups, okay, so RMON agents gather 9 groups of statistics, okay, 10 including the token ring, which are forwarded to the manager on request, usually via SNMP. So this includes statistics, okay, history, alarm, host top N, matrix, filters. We've got packet capture, events, and then of course the token ring. Okay. Now the statistics contain statistics such as packet sent, okay, byte sent, broadcast packets, multicast packets, the CRC or the cyclic redundancy check, okay, runs, giants, fragments, jobbers, and so on. So the history used to store periodic statistical samples for later retrieval. Now, the alarm is used to set specific thresholds for managed objects and to trigger an event on crossing the threshold. Okay? So the host contains statistics associated with each host discovered on the network. The host top N contains statistics for hosts that top a list ordered by one of their observed variables. The matrix contains statistics for conversations between sets of 2 addresses, including the number of packets or bytes exchanged between 2 hosts. Filters, it contains rules for data packet filters. Data packets matched by these rules generate events or are stored locally in the packet capture group. Packet capture contains data packets that match rules set in the filters group. And events, so controls the generation and notification of events from this device. So token ring contains the following token ring extensions like ring station, detailed statistics on individual stations, ring station order, order list, configuration information and insertion or removal data on each station, and source routing. RMON2. So RMON1 only provides visibility into data link and the physical layers. Potential problems that occur at the higher layers still require other capture and decode tools. So because RMON's limitation or RMON's 1 limitations, so RMON2 was developed to extend the functionality to upper layer protocols. So basically for RMON1, that caters only on the physical layer and data link layer. Whereas RMON2, that extended the capability of RMON1 up to the application layer. Okay? Now with visibility into the upper layer protocols, the network manager can monitor any upper layer protocol traffic for any device or subnet in addition to MAC layer traffic. So RMON2 allows the collection of statistics beyond the specific segment's MAC layer and provides an end-to-end view of network conversations per protocol. Okay, so the network manager can view conversations at the network and application layer. So therefore, traffic generated by the specific host or even the specific application, for example, a telnet, okay, or a web browser. Okay, so that can be observed. Okay, now the key point for RMON2, RMON2 is not a replacement for RMON1, but an extension of it. Okay, so RMON2 extends RMON1 by adding 9 more groups that provide visibility to the upper layers. Okay, so this figure here illustrates the RMON groups that were added when RMON2 was introduced. So this includes protocol directory, distribution, mapping, network layer host, network layer matrix, the application layer host, the application layer matrix, the user history collection, and probe configuration. NetFlow. Infrastructure. Cisco NetFlow is a measurement technology that measures flows that pass through Cisco devices. So NetFlow answers the questions of what, when, where, and how traffic is flowing in the network. So NetFlow data can be exported to network management applications to further process the information, providing tables and graphs for accounting and billing, or as to aid for network planning. So the key components of NetFlow are the NetFlow cache and data source that stores IP flow information, and the NetFlow export or transport mechanism that sends NetFlow data to a network management collector such as NetFlow collection engine. Now, the NetFlow collected data serves as the basis for a set of applications, including network traffic counting, usage-based network billing, network planning, and network monitoring. So NetFlow also provides a measurement based for QoS applications. It captures the traffic classification or precedence associated with each flow, so thereby enabling differentiated charging based on the quality of service. Now, comparing NetFlow and RMON, okay, so you've got the NetFlow versus RMON information gathering. So NetFlow can be configured on individual interfaces, thereby providing information on traffic that passes through those interfaces and collecting the following types of information. So you've got the source and destination interface numbers or addresses, input and output interface numbers or addresses, TCP UDP source port and destination ports, the number of bytes and packets in the flow, the source and destination autonomous system numbers for BGP, time of the day, and the IPTOS or type of service. Okay? Now, compared to using SNMP with RMON MIB, NetFlow's information gathering benefits includes greater detail of collected data. So, data time stamping, support for various data per interface, and greater scalability to a large number of interfaces. So, RMON is also limited by the size of each memory table. So, NetFlow's performance impact is much lower than RMON's, and external probes are not required. Applications using NetFlow. So NetFlows enable several key customer applications, including the following. So you've got accounting and billing. So because flow data includes details such as IP addresses, packet and byte counts, timestamps, and application port numbers, NetFlow data provides fine-grained metering for highly flexible and detailed resource utilization accounting. For example, service providers can use this information to migrate from a single fee, flat rate billing to more flexible charging mechanisms based on time of day, bandwidth usage, application usage, the quality of service, and so forth. So enterprise customers can use information for departmental cost recovery or cost allocation for resource utilization. So the next one would be network planning and analysis. So the NetFlow data provides key information for sophisticated network architecture tools to optimize both strategic planning, okay, and tactical network engineering decisions. So this has the benefits of minimizing the total cost of network operations while maximizing network performance, capacity, and reliability. So next one would be the network monitoring. Okay, NetFlow enables extensive near real-time network monitoring. So to provide aggregate traffic or application-based views, flow-based analysis techniques can be used to visualize the traffic patterns associated with individual routers and switches on network-wide basis. Now, this analysis provides network managers with proactive problem detection, efficient troubleshooting, and rapid problem resolution. Next would be application monitoring and profiling. So NetFlow data enables network managers to gain a detailed time-based view of application usage over the network. So content and service providers can use this information to plan and allocate network and application resources such as web server, sizing, and location. Okay, so that is just to meet the customer demands. Next would be the user monitoring and profiling. Okay, so NetFlow data enables network managers to understand customer and user network utilization and resource application. This information can be used to plan efficiently, allocate access, backbone, and application resources, and detect and resolve potential security and policy violations. So the last one would be the NetFlow data warehousing and mining. Okay, in support of proactive marketing and customer service programs, NetFlow data or information derived from it can be warehoused for later retrieval and analysis. For example, you can determine which applications and services are being used by internal and external users and target them for improved service. This is especially useful for service providers. So because NetFlow data enables them to create a wider range of offered services, okay, so a service provider can easily determine the traffic characteristics of various services and, based on this data, provide new services to the user. So an example of such service is the voice over IP, which requires the quality of service adjustment. The service provider might charge users for this type of service. Cisco Discovery Protocol, or the CDP. Now, this has the equivalent on the open standard. So we call it LLDP. Okay, so this one is CDP. Okay, now let's focus on the CDP, or the Cisco Discovery Protocol. So basically, CDP is a Cisco proprietary protocol that operates between Cisco devices at the data link layer. So CDP information is sent only between directly connected Cisco devices. A Cisco device never forwards a CDP frame. Okay? Now, CDP enables systems that support different network layer protocols to communicate and enables other Cisco devices on the network to be discovered. So CDP provides a summary of directly connected switches, routers, and other Cisco devices. So CDP is a media and protocol independent protocol that is enabled by default on each supported interface of Cisco devices. So would it be a router, access servers, and switches? The physical media must support subnetwork access protocol encapsulation. Okay, now this figure here illustrates the relationship between CDP and other protocols. Again, CDP is a proprietary protocol and can be used only on Cisco devices. Now, if you're planning to have the functionality on a non-Cisco device, then you can use LLDP. Discovering neighbors with the Cisco Discovery Protocol, or CDP. So how CDP works. So as illustrated in this figure, CDP information is sent only when directly connected Cisco devices. In this figure, the person connected to switch A see the router and the two switches directly attached to switch A. Other devices are not visible via CDP. So for example, the person would have to log to switch B to see router C with CDP. Okay? So CDP is a hello-based protocol. And all Cisco devices that run CDP periodically advertise their attributes to their neighbors using a multicast address. So these frames advertise a time to leave, or TTL value, the hold time in seconds. Okay, so that indicates how long the information must be retained before it can be discarded. CDP frames are sent with a time to leave value that is non-zero. So after an interface is enabled, so a TTL value of 0 is sent immediately before the interface is shut down, so allowing other devices to quickly discover lost neighbors. Syslog accounting. So a system message or error reporting service is an essential component of any operating system. So the Syslog system message service provides a means for the system and its running processes to report system, to a network manager. So that includes the state information. Now, Cisco devices produce Syslog messages as a result of network events. Every Syslog message contains a timestamp if enabled, severity level, and facility. Now, that severity level is denoted by these integers here. So, emergency, level 0. So, alert is level 1, critical, level 2, error, level 3, and so on. So, debugging, is at level 7. So, example of Syslog message is provided on this figure here. So, it shows a sample of Syslog message produced by the Cisco iOS software. The most common messages are those that a device produces an exiting configuration mode and the link up and down messages. If ACL lagging is configured, the device generates syslog messages when packets match the ACL condition. So, ACL lagging can be useful to detect packets that are denied access based on the security policy that is set by the access list or ACL. So, example of syslog messages. So, this figure illustrates the syslog distributed architecture. Syslog messages are sent to the console session by default. So a device must be configured to send syslog message elsewhere. The configuration includes the address of the NMS or other device. So network devices can be configured to send syslog message directly to the NMS or to the remote network host on which syslog analyzer is installed. So a syslog analyzer conserves bandwidth on WAN links because the analyzer usually applies different filters and sends only a predefined subset of all the syslog messages it receives. The analyzer filters and periodically forwards messages to the central NMS. For example, the analyzer could filter ACL lagging data from other router or switch syslog entries to ensure that the ACL lagging data does not overwhelm the syslog reporting tool. So let's have the summary of this subtopic or segment. So network management is supported with various devices and servers that use network management protocols and standards. So SNMP is a simple network management protocol that is the foundation of network management architecture. A MIB stores local management agent information on a managed device. So RMON is an MIB that supports proactive management of remote networks. So NetFlow collects network flow data to support network accounting, usage-based billing, planning, performance monitoring, and quality of service applications. The Cisco Discovery Protocol is a Cisco proprietary protocol that enables you to discover Cisco devices on the network. The counterpart is LLDP. So Syslog reports system state information based on preset facilities and severity levels. And for the module summary, we've talked about the hierarchical network structure that composes of access, distribution, and core layers. Based on the Cisco SONA, the enterprise or the Cisco Enterprise Architecture provides a modular hierarchical approach for providing network infrastructure and services to all places in the network. So network infrastructure services add intelligence to the network infrastructure, supporting application awareness within the network. So network management protocol supports the exchange of management information between the network management system and managed devices. So that's the end of the video. Have a great day.